We'll be talking about air temperature estimation with remote sensing and meteorological station.
Thank you. So good morning, everyone. My name is Rodrigo. I'm a meteorologist and PhD student at the University of São Paulo, and I'll be showing you my work on air temperature estimation with remote sensing in the weather stations in the metropolitan region of São Paulo. Um, we know that urban heat islands can occur in this atmosphere and on the surface. And those two urban heat islands are a bit different from each other. And these images illustrates that a little bit. On your left, you have the nocturnal canopy layer urban heat island, which means this is the near surface air temperature. And on your right, you have a cross section of the surface temperature in black and the near surface air temperature in red. And above you have the during the day and below during the night. And here you can see that the air temperature is smoother than the surface temperature. The air temperature is also advected with the wind, which doesn't occur with surface. And the difference between day and night is bigger in the air temperature, where during the day, the intensity of the urban heat island is very small, sometimes even zero. Whereas in the surface urban heat island, it stays active during day and night. And this is related to the fact that the atmosphere is a fluid, so it won't be heated just by the surface below it. It will be heated by all the areas it passed by before, and it can be approximated by a hypothetical source area, like is illustrated by these images. And then the land surface temperature is also obtained by remote sensing, usually, which has high spatial resolution and low temporal resolution, and it is the most used in urban heat island studies because of the high resolution and the low costs involved. In the other hand, air temperature is measured in situ at weather stations, which has low spatial resolution, and it is more related to human exposure to heat. So it would be important to have a high spatial resolution air temperature data. And its spatial patterns are different from those of LST, which is why there is no simple relationship to estimate air temperature from LST. But as LST modulates air temperature and vice versa with exchanges in heat, some relationship is expected between those two. So my objectives are to study statistical relationships between land surface temperature and air temperature and explore how the surroundings affect their correlation. So for that, I use data from the metropolitan region of São Paulo from 2008 to 2021, and remote sensing data from Landsat 5 and 8, and air temperature data from 51 water stations from 5 different managers. So the metropolitan region of São Paulo is located in South America, Brazil. It has 22.6 million inhabitants, which makes it the largest in Americas and the fifth in the world. It has around 8,000 square kilometers, and it is located near the Atlantic Ocean, but on a plateau 800 meters above sea level. This is an image just for illustration of the natural true color composition of São Paulo, where we can see the urbanized area. It has 85 kilometers wide around and 45 kilometers in latitude. The Landsat data summed up to 87 images that I used. The resolution was resampled to 40 meters. It passed around 10 a.m. in the local solar time, and LST was computed using Ermida algorithm. Here is an image just for illustration of the mean surface temperature in the wet season. I won't get in details on how I made this image. It's just for illustration. It will be another work I made. But here we can see the surface urban heat island of the metropolitan region. The weather stations I used are those one. Most of them are in the urbanized area, but some of them are outside as well. And the influence of the surrounding. So for that, I approximated those source areas I mentioned by a circumference around each station. And to estimate how they would be, I computed the mean land surface temperature in different circumferences around the stations. And then I computed the Pearson correlation for each radius, each station, and for a photo period less and greater than 12 hours. What the photo period would be the time the sun stays above the horizon during the day, and is greater than 12 hours when it is summer and spring, and less than 12 hours when it is winter and autumn, independent of the hemisphere. And clouds were removed using the CF mask algorithm. Here is just an illustration of how this would be, those circumferences. The dot would be the weather station, the grid would be the Landsat data, and the circumferences mark where, which pixels I would use to compute the mean land surface temperature. And the results, so I can show you all of the scatter plots, like there are 51 weather stations and a lot of radius ranging from 40 meters to tens of thousands of meters, like tens of kilometers. But I'll show you some of the cases where the correlation got a good increase. Not all of the stations got a good increase, but some of them got. Here we have a case for a photo period less than 12 hours, where the correlation got from 0.91 to 0.95. And here's a case for a photo period greater than 12 hours, where the correlation got from 0.6 to 0.87, a great increase in this case. Here now is a histogram of the Pearson correlation for all the stations for our radius fixed at 30 meters, which would represent the original Landsat data resolution. And here is using the radius where the correlation is maximum. So we can see that many of the stations got an increase in the correlation, but not all of them. Now I'll be showing you the spectrum of the correlation in function with the radius. Here are all the plots for each station for a photo period less than 12 hours. I will approach each one. Here are the cases where the correlation didn't change much with the radius. Here now are the cases where the correlation got an increase in large radii. And here now are the cases where the correlation got a double maximum, then cases with an increasing correlation, cases with decreasing correlation, and other cases where I couldn't match with the other groups. And now for a photo period greater than 12 hours, here are cases with a constant correlation followed by a decrease, cases with one peak in the correlation, and cases with constant correlation again, cases with a local minimum in 1 kilometer, like here, and a maximum in 10 kilometers, and a constant, constant and an increased correlation in large radii, and other cases again where they couldn't match with the other groups. So in conclusion, we see that the correlation changed with the weather station and the radius and the time of the year. The correlation is also greater with a photo period less than 12 hours. Correlation does not improve with radius for every station, but in some of them it got a great increase. And the radius of maximum correlation can be in small or great radius. And similar behavior was found among the stations, which is possibly related to similar surroundings around them, but that is still to be analyzed. And for the future, I plan to study more how the land cover and the wind and other variables might improve the correlation as well, maybe changing those circumferences I made to a more realistic source area. And if a general model is found, it will be possible to compute air temperature from LST finally, and determine as well air temperature hotspots in our cities, and also determine the hotspot source areas, which could help policymakers to choose where to focus in tree planting, for example, and other types of mitigation. Like you don't need to plant a tree exactly where the hotspot is, but also in these source areas as well. Those are my references, and thank you very much.